to talk about is what you have been hearing, you've been seeing, the new database systems that are in the space of Hadoop, Spark, Impala, whatever you have heard of, especially in recent years, because people see opportunities where there is a change in the database systems. Database systems has not changed much over the last 30 years, since late 70s until the last 10 years, triggered by the user companies. The companies were looking for cheaper solutions, were looking for solutions that is not bulky, that does not require people to do ETL, expensive ETL process. So they started to develop their own systems, and that changed the whole scene of database businesses to some extent. So we look at the catalyst for change, and you might have heard of it, and so we just quickly go through some of them. There are three factors that cause all these changes. First of which, as you know, is the data. The data is always the root of all problems. It could be the user-generated data, for example, the amount of data generated in Facebook, Twitters, and so on. Just a huge amount of data that has been generated. And today you can collect the data very cheaply, either through better automations, more efficient automations, or the IoT, for example. IoT is trying to roll out the network of sensors. With that, then you can collect more data. And you can store very cheaply as well because of falling prices of the media, of the hardware. And there have been many success stories on how people can exploit data. This gets people excited, even for non-technical people. For example, the doctors are excited about using the data to do predictive analytics such that they can save life. In fact, there's a recent success example that says that you can predict the heart attack 4 hours before it happens by looking at 72 vital signs and parameters such as heart rate, glucose level, and age, and all other things. Then they can predict 4 hours beforehand. Of course, it's not 100% accurate, but these sort of things get doctors and non-computer scientists excited about the applications of these database analytics processing. And in this data, since they come from different formats, they create a variety problem because we collect the data from multiple sources, so we end up with different formats. And unlike before, we used to only process structured data for business processing. Unstructured is basically for text processing, semi-structured is basically XML. Today, you collect all of them together and you want to put in one system rather than in multiple systems, and you try to process them as one, try to make use of the data from all the different sources. And apart from the varieties as well as the volume, there is the rate of the data being generated. It's generated very fast. In fact, if you look at this image that I have taken from the internet, for example, YouTube has about 48 hours of videos every minute. Just the amount of data it creates per day, per month, per year. The size is huge. In terms of the data that we have been using for our own research, for our own system development, for example, we are working with NUHS, which has about 2 gigabytes of data. These are data, mainly data fed from their systems or from their devices. And StarHub has about 400 plus gigabytes of data. This again, the data fed from their signal and other applications. When we talk about big data or huge amount of data, quite often people mistake it or equal it as just analytics. But in reality, it's much more than analytics. Before you can do any analysis or modeling, you have to do many things that are very expensive. They are not cheap, could be one-off. For example, you have to acquire the data. If you haven't got it, you have to extract, clean, cleanse, and so on, and integrate before you can really analyze the data. So you have to do all this before you can do analytics on the data. After you do the analytics, then you need the data scientist or even a very good visualization package for you to generate or visualize the data. So before all this, you need all other things to make up the whole package of big data and analytics. Now, apart from analytics, we forget about storage, we forget about platform for supporting processes, and this is the part that I'm working on. I'm working on both analytics as well as platforms, but more on the platform side than the analytics side. So analytics, in order to support analytics, you have many other components or modules in order to facilitate analytics, but you need a good storage systems as well as the processing engine to do that. We all know about big data and its definitions. The 3V means that volume, variety, and velocity. As usual, when you have 3Vs, there will be people trying to say, how about the 4th and the 5th and the 6th V? For example, velocity, values, and others. So how do all these V's affect the systems? When you look at the system core and the applications, which V's will affect the system core? Actually, only the 3 V's. The top 3 V's will affect how the system being designed and implemented. That is the processing engine part. And the other V basically affect the application. For example, we are looking at uncertainty. If the data is uncertain, you have to infer or make some inference. That could be done at the application level. Before you put in the data, or after you extract out the data, you want to infer some value out of it. And the value, how you extract the value, that again, it has to do with the application rather than the system itself. Now, as always, enough is never enough with the hardware advancements moving so fast. People want better systems, faster systems. So, speed is everything in business. They want the system to be as fast as possible. And want it to be interactive as well as providing fast response time. But on the other hand, the disk kills everything. This is still slow because of the mechanical scan and movement of the case. So it's still pretty slow. So therefore, you have to try to put everything in the memory as much as possible. And luckily, we have, these are what has been said by Jim Gray, is becoming true, that memory is the new disk is the new tape. Because memory is getting so cheap now, you can put everything, at least all the OLTP data inside memory. Of course, you can say like all the UGC data, because they are so huge, there's no way you can put all the videos, all the tweets inside memory. But other data like indexes, OLTP data, all can be dumped inside memory. That will give you the speed. RAMs become bigger and cheaper, so that make it possible. And if you look at hardware advancement, we look at the RAM itself, the price per megabyte has been dropping. We used to pay about 10,000 per megabyte in 1980. Today we pay less than a cent per megabyte. The hardware advancement drives the design of new database systems. Before that, we thought about putting the data into memory. Say, main memory databases is not new. We work on it since 1985, but because of the cost of the main memory and the size of memory, so it was not materialized then. But today, it's possible for us to put everything inside memory. And the number of cores per CPU, so the number of cores goes up. For example, in 01, you have only one core. Today, you could have hundreds of cores in one CPU. And of course, there are other advancements such as NVM, GPU, RDMA, remote direct memory access, and HDM, hardware transaction memory. So when we look at all these memory structures, it's different now. We do not have to worry about L3 cache, for example, 10 years ago. Today, most expensive systems come with an L3 cache. So when you move the data from, for example, from memory to where you want to process, you have to switch the data from main memory to L3 cache to L2 to L1 before it can be read and processed. And all these caches have different cache line, and they come in different sizes. So therefore, we try to structure the data such that they are cache friendly. Means that they can get squeezed in without increasing your means hit rate. So you want the hit rate to be as high as possible. Therefore, you have to structure it nicely such that it's friendly towards your cache and the cache line that you have. Another factor, as mentioned earlier, is the cost. And when all these startups, especially the search engine, social network startup, when they first start, usually they do not make money in the first few years. So they grab whatever free out there, open source out there, as they can to develop what they can use to implement the systems and to store and process the data that they need to. And also another thing is that when they crawl the data on a daily basis, they do not want to spend all the time to clean up the data, to load it into the system. For example, you have to load it into one of the current database systems, then you have to clean it, load it, and it takes a long time just to load. It is very expensive, it's very bulky. And all these companies want to run away from that and also run away from the cost. So therefore, that causes the users company to use the open source. Once they become riches or become big, then they start to think about developing their own system because the old solution does not meet their new requirement. For example, you look at Google itself. Google moved their clusters of MySQL 2 years ago to F1. F1 is the new distributed database systems that provide strong consistencies, that make use of hardware and to speed up and to provide the consistencies. So they run away or move away from MySQL to F1. It's the same from the MapReduce that they started with. MapReduce was just simple engine for them to extract the data, process it, get some statistics out of data. But as the company grows, the operations become more complex and they want to extract more and more values on the data, so therefore they start to implement their own new systems. As we often hear this, the only thing that is constant is change. And that is true. You look at database systems for 30 years. When we first started to have it in the late 70s until, say, early 80s. We hardly changed because of the hardware. Now the hardware advancements make all the changes possible, and the data and other things make that possible. When you look at the OLTP operation, typically only 12% of the processing power or the time goes to doing the real work. Lots of time that we have to manage the buffer because of limited memory. So you have to say what to be kept inside memory, what to be prefetched, what to kick out, and that costs about 31% of the time. And to ensure ACID property, to ensure that you have a consistent state in the database systems, so we need lock, and that again consumes another 31%. And suppose there's a failure, you want to bring back the database systems to a correct state. So therefore, before you write, you have before image lock, and after image lock after you write, such that if there's a failure, you can bring it back to the correct state. And that again takes up 30% of the time in processing. So all this takes up time, but with the advancement in hardware, people are trying to run away from having to do some of this or trying to reduce some of this such that more time could be spent on doing real work. When we have hardware, faster CPU, now we can compress the data inside the disk, bring back to the memory and decompress. So we make use of the CPU speed to trade off for the less I/O cost. So when you compress, the data is about 1/5 of the actual size. You bring back to the disk, so it costs 1/5 less. But you have to spend more time on the CPU side to decompress. That is fine because now CPU is a lot faster, so therefore people will do that. Compress, bring back to the memory, and decompress. And when we talk about storage structures, we used to talk about row structures or column-based structures. And what we are familiar with is the row-based store, which means that we store the data row by row. Row by row is good for OLTP sort of updates, but for OLAP processing, the column-based will be much better off because in OLAP, we tend to read the whole column at any time for any query, but just a few columns at a time. So when you read, say, like hundreds columns, you only use 3 columns. It's better to read just that 3 columns, and therefore column-based is always better than row-based for OLAP. But for OLTP, because you update one tuple at a time, therefore the row-based is much better off. Before that, we know all this, but because of hardware slowness, and you can't really possibly play with the states that I'm going to compress, bring back to the memory, and decompress. But today, that is possible. In fact, most of the vendors will start to store data in the column base, in the disk, if they have to, and bring back to the memory, suck in the memory, and reconstruct on the spot, basically to support much faster OLTP. And with an increasing memory size, we can now store everything inside memory, and therefore we have in-memory databases for transaction memory. The hardware side will provide us faster concurrent accesses, provide some form of semaphores for us to access the data, to protect the data in concurrent accesses. With a multi-cores, we can have but 1 thread per core. Then the argument is such that when you have 1 thread per core, there is no contentions. There is no lock-in required. If you structure your data properly such that 1 thread only per partition of data, therefore it can clear the processing much faster without having to lock, or at least not as heavy as before. And with more and more compute nodes that we can afford, just like Google used millions of nodes because those are cheap. Each node can cost about 1,000 today or 2,000 at most. So you can see that 1,000 nodes is about 2 million. And that is cheaper. So for that, then you can end up with a scale up. Instead of buying parallel machines, now you buy huge clusters of nodes, cheap nodes, commodity nodes that can do the scale up and execution parallelism. Once you have more nodes, of course, you can replicate more. And up to 3 replications, you are quite sure that your data will never be lost. Your uptime is about 100%. We all know that parallelism breaks bottleneck. From 2nd year or 3rd year onwards, we start to hear that suppose you have 1 skip list, and everyone got access the head of skip list to get a free slot. But if you break up the skip list into 3 or 4 sub-skip lists, then you can always go to one of these to find the free slot. So parallelism does breaks bottleneck. And therefore, the more nodes we have, the better it is. And that is parallelism. But today, we can exploit parallelism at 3 levels. At the data level, instead of SISD, now we can go for SIMD. Single instructions, multiple data. So in that case, so long as the algorithm can work on vectorized data, we can have just one instructions, process a few data items in one go and produce a result. For example, if you store it in column-wise format, since you store only one column, you can process it 5 or 6 outputs, but one attribute each time, and therefore you can do that and come out very quickly. In terms of shared memory, scale up, because we have multi-core, so definitely you can always scale up with more and more nodes inside your CPU, more and more cores inside your CPU, you can have more threads, and some of which you can even go for hyper-threading, and therefore that will speed up. In distributed systems, we often talk about scale out, not scale up, because more nodes, then you start to scale up. If you need less node, you collapse back, and as we know, in these systems, we can have data partitioning the data such that each node handles one partitions, and at the same time do the same executions or similar execution as others, and that's where we achieve the partition execution. So what are the opportunities when we all these changes? Now, in 2004, Google came up with their Hadoop MapReduce systems. The open source is Hadoop, developed by Yahoo. So it was pioneered by Google, mainly to process 20 petabytes of data each day. They do not want to clean the data as they crawl the data. If you have to clean it, you will spend much longer time to clean it just to process it. So they want to be able to crawl, store, and quickly extract what they need to, provide some, and then to gather some statistics. That's what they want. That's what MapReduce was initially proposed. For example, to do their PageRank, they need to know what are the references and so on, from which page reference which page, and what are the keywords in each page, and how frequent they happen. And popularized by open source Hadoop, such as Hadoop, so used by Yahoo, Facebook, Amazon. It's simple and reliable. It's a very simple everything, so long as you can map into map and reduce functions, you can run the program. So it basically consists of the distributed file system that handles the distributions, and then the MapReduce will just read, extract, and process. So it manages the work, distributions, and fault tolerance, but it's not efficient and flexible. It's not flexible in the sense that whatever you want to do, you have to map it into map and reduce functions. So anything that's iterative will take many MapReduce phases, and therefore it's not efficient. So when you look at MapReduce, it has its own strength. It was designed for what it was designed for. For example, it provides clean abstractions for programmers. Then it has automatic distributions and prioritizations. It provides good fault tolerance. And programmers just need to learn how to program map and how to program reduce. So long as you can transform what you want to do into map and reduce, you can run MapReduce very easily. It's not expensive as compared to a typical parallel database system. There is no expensive ETL. You don't have to extract, transform, and load. Loading part is the killing part for parallel databases, for any commercial or relational database system, for example. And the data also is not structured. The data could be just text, could be semi-structured, could be even relational. So what they want to be able to do, I read the data in, interpret on the spot, extract, and get what I want, and do some statistics gathering. And it's built on top of a commodity hardware. So there's no expensive hardware as required by parallel databases. For parallel databases, you need very expensive blocks. CPU, you want to scale up, you have to add in more CPU, shut it down, put the CPU in, and reboot it with a new configuration. So it's much more troublesome as compared to a MapReduce architectures. For MapReduce, it's easy. You can add in more nodes. The system will try to scale up on itself. So for example, today you can have 10 nodes, tomorrow 20, 30. When you need less, then they will try to do the distributions of the resources as well. But whatever you have, people try to use it like database systems, because after popularized by Google, and then because of open source Hadoop, people think that, look, Hadoop could be used for all sorts of things that I want to do with a typical database systems. And they start to complain as well. They complain that, for example, there's no index support, there's no B plus tree, whatever indexers you know of. When there's no index, what does it mean? It means that whatever that you want to search, whatever you want to retrieve, you have to scan the whole database to get one or two items that you want. That is a problem without index. And there's no schema support. Everything is in free format. So long as I know where to read, what to extract, it works. And there's no schema, nothing like that, so I do not know what are stored inside the data set, what are being stored there, and how can I query. Everything is based on keywords or based on some predefined MapReduce functions. There's no high-level query language. There's no SQL-like language. And later on, of course, Hive was introduced by Facebook, and Pig Latins was introduced by Yahoo. The performance, also people argue that, look, I do not need thousands of nodes. For the same performance, I can do it with just 50 or less than 100 nodes inside the parallel systems. Means that you just have 100 CPU, it could achieve the same performance. But again, this is a cost problem, because the cost of a parallel system is expensive by itself and is more tightly integrated. And another problem of MapReduce is that the communication cost is high. Each time you read in, you process the map. After you process the partial result, you have to push to the nodes that are doing reducing. When you push, you're doing the shuffling cost is the most expensive cost in this case. After you do the reduce, you have to write back to your distributed file system, HDFS or DFS. So you have to write it back, and that contributes your cost. So therefore, it's not fast, it's not efficient in that sense. And because of that, many of these mechanisms, such as index, schema supports, all those were introduced over the years. And we have a recent survey papers that published in ACM that details all the developments of MapReduce-based systems, from MapReduce to Hadoop to Spark in recent years. In 2010 and 2011 in the panel, I argued that, look, MapReduce is MapReduce. If you try to use MapReduce as a database system, don't complain. It's just like we have bus. Bus is meant to transport human beings, passengers. But if you try to use bus or use truck to transport human beings, like for example in Singapore we allow trucks to transfer workers around. Truck works well as a bus, but it's not comfortable, it's not safe. When it rains, you get wet and so on. And the problem is that the truck was built as a truck to transfer cargo, not passengers. The bus is meant to move passengers. So the two are not equal. And you try to use a truck like a bus, then you deserve the problems that come with the truck as a bus. It's not comfortable, it's not safe, and so on. And might not be as fast as a bus. So that's the same here. If you make the comparisons between the two, MapReduce was never designed as a database system, although it was designed to process huge amount of data, but was not to process a huge amount of data as in typical database systems. And therefore, a bus is a bus, a truck is a truck. It's the same case for MapReduce versus the database systems. In 2011, this is a landscape that we have. And we have Amazon, SimpleDB, Peanuts, Cassandra, and so on. And MongoDB was started around that time as well. It's a distributed document systems. You manage mainly JSON and JSON files. Today, even for MongoDB, it's worth of value at 1.2 or 1.3 billion. So the company's grows and start to have many users. But all this landscape has changed, even for the last 3 years. Today, we can see more systems. Suppose you classify into either it's for graph, this side is for in-memory, this side is for disparate, this side is the one that make use of NVM. And we classify into either it's for graph, this is a graph engine, these are the stream processing engine, these are the main memory, typical database processing engines, and this is just a memory management, this is a storage management. If you classify that way, this is the new landscape that we have. And our efforts include Epic, log-based, ES2, and the Epic engine. And of course, we have a new system called NashDB. Actually, that is just our main memory, in-memory Epic. And we are moving all to one such that we focus on in-memory. We have our new memory management, but also store the data in the NVM instead of into the disk. And again, if you want to read the survey, you can find the survey here. You just completed, you can submit to someone. The shocking news is that in June this year, the senior VP of Google came out to say that they dumped MapReduce a few years ago. And that put many companies that make use of MapReduce or Hadoop or who promote their systems or MapReduce-based systems, put them on the spot. Because if Google stopped using MapReduce a few years ago, why should we spend so much time in trying to improve MapReduce or Hadoop? That means that there's something wrong with the MapReduce. Therefore, even today, the creator no longer use MapReduce. It says that they stopped using it 3-4 years ago, and today, for example, they have F1, they have Photon, Dreamer in place of MapReduce, in place of clusters of MySQL. Whatever we want to do, we can't run away from designing systems that satisfy these three requirements. We want the system to be as fast as possible, there's latencies. We want it to be up all the time. There's availability, and we want it to be reliable. When you submit a job, it has to be written within certain time frame that we are happy with. Not only that, if there's a failure, it should be able to recover to the correct state very quickly. So we can't run away from latencies, availability, reliability for any system that we want to design. And of course, there have been approaches trying to achieve all this. For example, trying to use in-memory storage to store all the data inside memory and to do the in-memory processing instead of store the data in the disk format today, because you assume that your data stores inside memory. When you run out of memory, you have to flush it to the disk temporarily or to the next media. So instead of convert into the disk format, you store back to the disk in the RAM format, such that next time you want to fetch the object back, you fetch it back without having to convert to the RAM format. Because whatever you store inside memory, whatever you store in the disk, they have different format if you want to search on the disk. And that's what we call ND-caching. And column store, as I said, is very good for OLAP processing, but even it's good enough for OLTP processing. So whatever we have today, that has been implemented by some existing vendors. For example, VaultDB is a new company, and SAP now there is a new system called SAP HANA that makes use of in-memory as a column store. SQL Server used to have their research system called Hackathon. Today, that has been moved to the commercial phase. They call it in-memory SQL Server. They have included in-memory storage and processing as well as column storage for their data. Of course, people are trying to reduce as well as much login overhead as possible. Login is required for recovery purposes, but login is very expensive. Just imagine you have to, at certain timestamp, you have to store the snapshot, and for whatever changes, transaction that you are running, you have to keep a record somewhere, so that if there's a failure, you can recover and repeat or redo what has been done. So that's the purpose of logging. But the logging itself is very expensive, and people try to reduce it. Instead of use transaction-based, instead of use a database logging, people try to use a command-based logging. Command-based logging means that you store the transaction ID or the stored procedure ID, say that I'm going to run these transactions or procedures, so that if there's failure, I just rerun that procedures. But to do that, then the recovery is expensive. But that is with the assumptions that the systems hardly fails, not as often as it might happen. And we need to have efficient transaction management, so we have to remove or reduce locking, latching. That again depending on how we're going to manipulate or play with the threads and processes or cores. That depends on how we do it, such that we can reduce the contentions. Once you reduce the contentions, you reduce the locking. Next, I will talk about very quickly about what we have built so far. Basically, it's a whole system that has been built. We built it for the last 8 years or so, 6 years or so, and it's complete. It's for use, and also if you have any use, do talk to me. These systems that we have built will be used for the collaboration project with StarHub as well as NUHS. We started to look at MapReduce around 2007 to 2008. Before that, I was working on peer-to-peer distributed systems as well as parallel systems. So we seriously to look at MapReduce sort of systems only from 2008 onwards. So that's why when we first started, we just tried to enhance MapReduce like others. Analyze MapReduce, turn the MapReduce inside out to look at what are the problems when MapReduce is so slow, and therefore, in fact, we have a benchmark Hadoop performance in 2010 VRDB. And subsequently, we propose different sort of optimizations and so on. And 2008, while we are doing that, we started to build our own systems. We use Calligraph-based index, and we have elastic storage, which was started, in fact, and one guy here, QQ, who started it, but this is the third version now. It's the third version. So quite often when you cut a system, because postdocs or RF research fellows come and go, after a few years we need to recut because of the changes in people as well as there's a new demand, a new requirement. So this is the third version that we have, and in fact for E3s is also the second versions that we have now. And in 2011, we started to build log-based structures. There are other log-based structures systems as well, such as RamCloud from Stanford, but RamCloud is not a transaction management system. Well, ours is, but on the other hand, we don't store everything inside memory. RamCloud stores everything inside memory. So there's a difference between two systems. but at this moment we are recoding it into an in-memory systems. This project is funded by A-Star, while EPIC was funded by MOE, and as well as at the later stage now funded by NRF. So recently, since last year, we have been looking at in-memory system. We look at relics, we look at memcache, we turn the system inside out to look at what works, what does not work, and try to figure out what to do. Suppose we have to design and implement a new system. So today we are building a database systems without system calls. System calls are very expensive. For every database operations, for example, read, write is a system call. So we try to use memory map to run away from system calls. We try to use RDMA to run away from TCP/IP call, write directly to other people's memory, and so on. And as I said, we are working on new memory management systems, which will be presented at next year ICVE. Data come in different formats. They come in either in the format of unstructured, semi-structured, and structured. We do not consider images and those block files because we cannot really process those block files. We have to take them as a block file. So for those we can understand, can manipulate, there are basically three types: unstructured, semi-structured, and structured, relational, XML, and text. And how to process all these data within one system? It's possible, suppose, to have three different programming models. So these three different data types favors different programming models. For example, for plain text, MapReduce is good for plain text. You read it, extract, map into what you need to do, then you execute. But MapReduce does not support iterative computations. For example, many of the social networking data are graph. MapReduce cannot process graph efficiently. That's why Google came out with their own Pedro systems. That is to process graph data. Graph data require lots of iterations, and you need Pedros. Relational data is dry add, is a DAG-based processing. So we have a mixture of models involved. You can use multiple programming models, and you can use, for example, Hadoop dry add output into one. This is one example that I took from the web. You can build a system by stacking all the open source and build a system or business out of it. But the reality is that all these integration of system, putting the system together, is not as straightforward as it seems, and it's not seamless. There will be gaps, there will be performance penalties, whatever you put in. Even for this one, the MacHub came out to say that, look, their new versions will not support anything that runs on Hadoop. So basically, these diagrams now can't be used. I have to run quickly because I have 5 more minutes to go. So what we want to do based on what we have here, we want to design systems that is flexible, that is optimizable, and that is extensible. We say that MapReduce is not flexible because everything got to be transformed into map and reduces. It cannot support iterative computation efficiently. For example, it cannot support like what Pedros support. Optimizations, while MapReduce allows optimization. For example, you can turn Hadoop to Hadoop to remember the states, to do the state processing, stateful processing rather than stateless processing. And we want it to be extensible. Means that so long as you have new programming model, new need, we should be able to map into what we have to support your need. So with that, we have 2 kinds of abstractions: concurrent programming and data processing. So at the lowest level, it handles all the computational needs, communication between computational units, how to parallelize all these units, and at the processing level, we have the different cut features. So long as you can define it in the actor programming model, we support it. So in this case, we use actors, and so long as all the computation can be decomposed into all these actors, we can support the computations. For example, MapReduce, we can do it with just 2 units in our systems, and for the DAG processing, such as dry add, we can use it in 3 units, like single table scanning, join, aggregate unit, and for this PPC query 3, we can do it very easily as well. For Preview, we can do it as if the unit is sending a message to itself. Then we can parallelize it, and we have a master node that handles the parallel processing, the scheduling of all these slave nodes. And each slave node will just process the data that it has. Once it's done, sends a message to the master node. The master nodes will inform whoever have to pick up the data from that node. For the experiment study, I only show one graph here. So in fact, you can see that for 2 other systems, such as Shark is Spark analytic systems, Impala is from Cloudera. Both are in-memory systems. And even when you compare to in-memory systems, we are much more efficient than Spark or Shark, but we are slower than Impala. That's basically because Impala is an in-memory systems. It's not open source, so we do not know at the moment what's inside that Impala. But on the other hand, Shark or Spark is an open source, so we can really analyze the systems. Although it's an in-memory system, it's slower than our Epic system. But our Epic at this moment is still a disk-based system, although we try to convert into an in-memory system. We have finished the whole stack. So we have finished all the components and building tools, for example, on the Epic graph, the graph engine. These are our execution engine. This is our trusted data service that will encrypt that you need to, and then do the encryption-based processing. This is our storage engine, and we have a performance monitoring tools that will do the RPC, extract out all the information to monitor the health of each component. On top of the stack, at this moment, we are building the healthcare analytics for NUHS, and as well as for StarHub. And of course, as I said, we're open to any companies or any collaborators who want to use the system. For example, there's a guy who wants us to use these systems to analyze the cybersecurity attack to the data, want to even analyze the malware and all this stuff. This is something that we like to do. After we build up the core engine, definitely want to have as many applications as possible on top of the engine. In Singapore, as I said, it's been used partially by NUHS, StarHub is still ongoing, and in China, we use it for CityCloud, which is a smart city solution company. We are working with a Zhejiang province finance department. This is like their Ministry of Finance, but it's at the province level. NetEase is the social networking company, and we are copying Southern power companies for their smart grid. So these are the ongoing projects that we have, and this is an example of what we do with the medical informatics. We put in humans as well to do the crowdsourcing, but the crowd are the doctors, and we provide the human machines interface or systems data processing. And at this moment, again, we are building this mainly for the users. So, for example, the doctors can go through, the programmers come in through the SQL plus R script. We translate, process, and pass back to R if we need to use R to further analyze it and visualize it. So, in summary, the 3 factors affect drive all these changes are the data, the types of data, the volume, the variety, the speed that the data is generated, that cause the changes of the backend systems. The hardware, usually we are driven by the hardware. When there's a new hardware, we try to exploit the new hardware. And the graph demands. People want different systems. They do not want to spend all their time to do ETL. They want the system to be as fast as possible for different needs, for different applications. And for these systems, whatever we build, we have to satisfy the three requirements: latencies, availability, reliability. Whatever we do, although people claim that, some people argue that big data is a hack. No matter what it is, at the moment it creates the awareness on the value of the data, and people recognize that the data itself could be used to gain innovations, to have a competitive advantage, and to improve productivity. For Epic, it's in the space of modern database management systems. It's efficient, flexible, extensible. Thank you, and if you want to look at some of the relevant publications, they could be found in my homepage.